Today I will show you how to find the position and velocity functions of a particle with a given acceleration function and initial conditions shown here. So this function here represents the acceleration of a particle with respect to time, and it is written as a vector-valued function. It is parametrized with the variable t representing time. So the first thing to do is to find the velocity function. So the acceleration of something, here it's just a vector value function, is the rate of change or the derivative of its velocity with respect to time. So with this derivative, we can solve it like a differential equation to work our way back and take the dt to the other side to separate the differentials. Then we can integrate both sides. And this differential of velocity is integrated, so it just becomes the velocity function. And that's the integral of the acceleration function up here, which is 2 to the e 2 times e to the power of t in the odd direction, or x direction, minus 4 times e to the 2t in the j or y direction, plus sine of 2t in the k or z direction with respect to time. Now if we integrate this, the velocity function turns out to be two times e to the t plus c1 the I direction, plus negative 2 times e to the 2t plus c2. So since we're integrating without proper bounds, we leave the constant for each term for each direction, like they're being separated. And this is in the j direction, represented with the hat. They're each all these are unit vectors, plus negative 1/2 times cosine 2t plus a third constant in the k direction. So without yet applying this initial condition, this is the velocity function. So if the time is 0, so t equals 0, then v at 0 equals 2 times 1, because anything to the power of 0 is 1, plus that constant in the odd direction, plus another, the 2 here, it doesn't matter anymore because there's 0, they're multiplied. So this is e to the power of 0, which is 1 again. So it's negative 2 times 1 plus the second constant times the j unit vector plus negative 1/2, and cosine of 0 will be 1 plus the third constant, the k direction. And since this is velocity at 0, it's also equal to the initial condition. So this is the same as I minus 4j plus k. Then we can turn them into something like a system of equations, where it's not exactly, but we're going to get 3. The I, j, and k one. So the first one is going to be 2 plus c1 equals 1, because that's a coefficient of I in the initial condition, which gives c1 equals -1. 2 plus c2 equals -4, and that means c2 is equal to -2. Lastly, we do -1/2 plus c3 equals to 1. That would mean that c3 equals to 3/2. So with this in mind, we can rewrite the velocity function as this. Velocity dependent on time equals 2 times e to the t plus c1, which is -1. The I direction plus -2 times e to the 2t plus c2, which is -2. In the j direction plus -1/2 cosine 2t plus the third constant, which is 3/2, in the k direction. Now, let's find the position function using the velocity function in a similar way that we found the velocity function with the acceleration function. Okay, so the velocity is the rate of change of the position. So velocity is the derivative of position. Let's say position is r, respect to time. Then in the same method, we bring the differential of time to the other side and integrate both. Now, the function of position equals the integral of the function we just found of velocity. So I'll write it separated instead of just writing one big integrand. Just like distribute the integral and the differential of time. So it's the first integral in the I direction is 2 times e to the t minus 1 dt plus the integral of -2 times e to the 2t minus 2, that's in the j direction, plus the integral of -1/2 cosine 2t plus 3/2 t in the k direction. We get the position function of 2 times e to the power of t minus t plus the first constant, the I direction, plus negative e to the 2t minus 2t plus the second constant, the j direction, plus -1/4 times sine of 2t plus 3/2 times t plus the third constant in the k direction. So again, we apply the initial condition of position and time equals 0. So r of 0 equals 2 times 1, because it's e to the power of 0, so I'll just omit the ones this time, minus 0, plus c1 in the I direction plus another 1, so negative 1, minus 0 plus second constant in the j direction plus sine of 0 is 0, so skip that, and that's also added to 3/2 times t, and t is 0, so it's 0 plus 0 plus c3, so it's just c3 in the k direction. And that's equal to I minus j. So from this, saying again the little group of equations, 2 plus c1 equals 1, negative 1 plus c2 is negative 1, c3 is just 0. So from this group of equations, we can find the constants at c1 is negative 1 and c2 is 0. So if those are plugged back into the position function, we get that r of t equals 2 times e to the t minus t minus 1, the I direction, plus negative e to the 2t minus 2t and no other constant in the j direction, plus negative 1/4 sine of 2t plus 3/2 times t with no constant, the k direction. This is how you find the velocity and position functions with an acceleration function and initial conditions. I hope this helped.